Real numbers. This is where computing can get really interesting, okay? So what do we mean by real numbers? A positive or negative value consisting of a whole number plus a fractional part. Let's have a look at what I mean. So 36.6278. Okay, consisting of a whole number, all right, and then consisting of our fractional part. So these are real numbers. Now the float and double data types, these are what we will use in Java, and I say that it's an abstraction of the real numbers that accept. Yes, that's what it is. So we use float and we use double when it comes to real numbers, okay? Integers are integers, real numbers are real numbers. And something just as a side note to keep in mind within the computer, 1 and 1.0. Integer, real number, okay? Really important because floats, doubles, integers have or can have different memory size allocation. Now, the range and the accuracy of our real numbers within a computer are limited. And I think sometimes people forget that. We think the computers can be really precise, and they can. But there's still a limitation to that accuracy. For instance, if you think of 1/3, okay, represented as 1/3, okay, or the square root of 2, again, represented as in just that format, we can live with that. But when we actually do a calculation with those, it becomes a little bit more complicated. So what we do, how does it get, and so you can see that, determined by the number of bits and the split up of the mantissa and exponent. Whew, that's a lot, isn't it? So the range has to be limited by definition, okay? An infinite number of bits is needed if we're going to represent an infinite number. So our accuracy is limited, all right? And it's important that we grasp this. So the number of significant digits that we can do is limited. So there are an infinite number of real numbers. If you think about it, we have an infinite number of real values, I should say, between any 2 points on the number line. We have a number line. If you're thinking, what's the number line? I'll say 0, 1, 2, 3, -1, -2. Between this point and this point, there are an infinite number of spots. That's just what there is because of the way we can go about doing it. We have irrational numbers. There are recurring decimals, okay? How do we represent this within the computer? Well, we represent it using the IEEE 754 form, okay? How we go about doing things in binary with these kinds of numbers. I'm going to quickly go through this in this next section, okay? And I'll tell you up front, there will not be any questions in the assessments about this. But it's important you have an understanding of accuracy within computer memory because it's tragically been this inaccurate representation within memory that has caused some catastrophic disasters. So we have the sign, obviously, the exponent and the mantissa, our significand, okay? We're going to use the single precision, which is binary 32, okay? And our sign bit is our most significant bit, 0 for positive, 1 for negative, nothing new. The exponent width is 8 bits, and we say bias to 127, which you'll see how that works as we go on. We've got our mantissa, our significand, precision, 24 bits, of which we explicitly store only 23. What? Okay, so this is what it looks like when we're doing single precision with 32 bits. We've got our change colors, our sign, we've got our exponent and the mantissa, all right? So let's have a look. And I've put that up there so you can see it. where you should be referring to when we do strict conversions. So to convert a base 10 real number into the IEEE 754 binary 32, this is what we do. Okay, here's the number we're going to work with, 12.375. So we determine the sign bit, positive, so it's 0. We convert the integer part to binary, 12, which is 1100. And now we convert the fraction part into binary, okay? So 0.375 is 0.011. Simple. Let's see how we got to it, okay? So we multiply the fraction by 2. If our value, when we do that, is greater than or equal to 1, we write a 1 to the mantissa, okay? Then we subtract 1 from the value, all right? Otherwise, what we're going to do is write 0 to the mantissa and repeat the preceding steps for the appropriate number of significant bits. And we stop if the value is 0 after subtracting 1. What? When the required number of significant bits is reached. And you're going, David, I'm a bit lost. Here we go. 0.375. We've got our calculation, the result, and the mantissa. So you remember what we did. 2 times 0.375, 0.75. Our mantissa is 0. 2 times 0.75, 1.5. Our mantissa is 1. Okay, it was great. The result was greater than 1, remember? So 1.5 subtract 1 is 0.5. And now 2 times 0.5 is 1.0. Our mantissa is 1. 1.0 subtract 1 is 0. We are done. And that is how we got that 0.011. Okay, now I realize that was quite a bit to it, but it's important just to get a bit of an understanding how we go about doing this. So now we've got to that, we're going to add our two results. So we had our 1100 and our 011. We add the two results. Now we've got to normalize them. So to do that, what we do is we move our decimal point until it is right of our significant bit. There, 1.1000011. Okay. We moved that 3 places, and now we use this for the base 2 exponent. All right, 2 point that times 2 to the power of 3. So our exponent is based on precision, 127 for a single bit precision, 127 plus 3. Convert to binary. We grab our mantissa, 10011, remember, and our final encoding is like that. As I said, it gets pretty complicated, but it's important that you have an understanding of it. Talking to some of my colleagues, they've never actually had to do this, but it depends where you go in the computing world whether or not you will need to do this. So it's important to understand that real numbers are very difficult to represent within a computer system.